currently here. Okay, all right. So in yesterday's lecture, we have discussed about the standard enthalpy change. Okay, so the reason it is called standard is because of the experiment ataupun the reactions are carried out at standard conditions. Okay, all right. So please do take note that the enthalpy change depend on all of these conditions. Okay, it depends on the temperature, external pressure, physical state, concentration of the solution, and the type of allotrope of the substance. If any of these is altered, that means the delta H will also be changed. Okay, all right. So these are the standard conditions. So if all of these are complied, that means the enthalpy change is considered as the standard enthalpy change, where we have not. Okay, dekat hujung H2. Okay, moving on. Okay, and then we have three types of standard enthalpy change. Okay, we have the first one, the standard enthalpy of formation. Okay, so you have to refer to the definition for the standard enthalpy of formation. You have to make sure that the mole of substance that form must be in 1 mole. It must be 1 mole, and then the elements, the constituent elements, okay, the reactants basically, they must be in their constituent element. Maksudnya dia punya state is element state and the standard state. Okay, in their standard state under standard conditions. Okay, all right. So these are the example of compounds and the enthalpy change or the formation. Okay, and then we have example here, carbon monoxide, and then we have checkpoint. Okay, so please check your answer with the answer given here. Okay, so you have to write the thermochemical equation to represent the standard enthalpies of formation for the following substances. Okay, all right, so sodium hydroxide is the substances, and then the question also specify that the state of sodium hydroxide must be in solid state, and this is the standard formation of standard enthalpy formation, and the value is given. Okay, right. Okay, so this is A, right? So this is A, so sodium in solid state, and then the oxygen must be in O2, because for oxygen, the standard state is O2, not O atom. Okay, it should be O2 molecule, and it must be in gas state. Same goes to H2. Okay, so you cannot just simply give sodium and then OH. That is not constituent elements. This is what we call elements. Okay, O2 and H2. And then to make sure that they are balanced, okay, because we cannot alter the coefficient on the product, but we can alter the coefficient on the reactant side. So to make it, to make the equation, so to make the coefficient is equal to 1, okay, we have to add in coefficient of half for hydrogen and oxygen, because this one later, okay, can be cancelled out, and they will have the same ratio on the reactant and also on the product side. Okay, but not to forget the enthalpy change, because we are talking about thermochemical equation. Okay, if you have only the equation, then it is known as normal equation. The reason it is called thermochemical equation is that you include the enthalpy change, right? Okay, so B, liquid ethanol. So we have carbon, hydrogen, and OH. Okay, make sure you don't forget to include the state. All right, so the rest are all the same like what we had earlier in the previous slide. So for the carbon, you must be using graphite solid, and it must be in graphite state. The allotrope is graphite, not diamond. Okay, you have to specify. For carbon, you have to specify. Then hydrogen. So hydrogen, you need to be in H2, and same goes to O2. Okay, and then you balance it. So we have 2 carbon on the product side, therefore we add in 2 on the carbon on the left hand side, on the reactant side. And then we have 6 hydrogen on the product side, 5 plus 1 is 6. So we place in the coefficient, the 3 coefficient on hydrogen, and then we have half on the oxygen. Don't forget the enthalpy of formation. So the reason we have kg per mole here, because this is formation. By definition, okay, the formation of the substance. So kg per mole of the substance form. Okay, so the enthalpy change can be given in terms of kg per mole, and sometimes you may observe in kg only. But if it's kg per mole and then it is specified here that it is formation, that means the mole is actually referring to the substance. If not, if you have somehow dia tak ada the formation, okay, dia tak ada formation, and then you kena find, you kena apa nama tu, identify sendiri. Okay, is this formation reaction? Yes, it is. Then it is understood even though it is not stated. Okay, so faham sendiri that this is the enthalpy change of formation. And then this is kg per mole. Dia boleh juga bagi kg, tapi it is understood. Faham tak? Dia tak perlu bagi benda tu perfect macam tu. Dia boleh bagi delta H0 and then negative 4 to 6 kg. Okay, when you refer to this equation and you notice that, okay, this is formation because all of these are in its constituent elements, okay, and then the product form ataupun the substance form is in 1 mole. Therefore, automatically it will be kg per mole of the product form. Okay, so sebab you jangan lupa to form this product, it requires 1 mole of sodium, half mole of oxygen, half mole of hydrogen gas. So this is not only for sodium hydroxide. This is also applicable to others as well. Faham tak? So if we are talking about negative 4 to 6.7, it is also for 1 mole of sodium, and then it is also for half mole of oxygen, and it is also for half mole of mole of hydrogen, and it is also for kg of 1 mole of sodium hydroxide. Okay, so don't forget that. Jangan lupa, sebab after all they come from the same balance equation. In order to have this reaction, you have to have these 3. Same goes to B. Okay, so sometimes janganlah pelik bila dia nampak sometimes dia kg per mole, madam. Sometimes kenapa dia kg? Okay, you boleh translate sendiri on your own. That's why you kena faham dulu apa maksud delta H formation. This is the amount of heat released for the formation of sodium hydroxide. Okay, so since sodium hydroxide is 1 mole, therefore dia boleh pakai kg per mole of sodium hydroxide if we are referring to sodium hydroxide. Okay, since we are talking about enthalpy change of formation, then it should be kg per mole of the substance form. Okay, kalau kita bagi general macam ni saja, so kita boleh letak macam ni. Boleh, tak ada masalah. Ni kita tak ada H. Okay ke? Okay ke guys? Please respond.
Madam tadi lag.
Tadi lag.
Lama ke lag?
Baru je.
Okay, alright. So, sekejap ya. So, how about now? Tak nak. Okay, saya kena tukar kepada data saya. Saya tak nak ambil risiko, okay, buat penat saya because I'm not going to repeat. Okay. Okay, saya keluar sekejap. Keluar sekejap. Okay, jom, let's continue. Okay, share the screen first. Okay, all right, so that's that. So that one is for enthalpy change of formation. Now let's move on to enthalpy of combustion. Okay, enthalpy of combustion. So the enthalpy change for combustion is when 1 mole of a substance is completely burned in excess oxygen under standard condition. So this is how you denote the enthalpy change of combustion. Okay, you have C. So you replace the F just now with C ataupun you add in the C. That stands for combustion. Okay, so 1 mole, so it is specified here that the substance that need to be burned must be in 1 mole. So it will be completely burned in excess oxygen under standard condition. Okay, if we have not here, that means the condition must be at standard. Okay, so these are the example of enthalpy change, standard enthalpy change of combustion for several substance. Okay, so we have hydrogen, benzene, aluminium, carbon, and then others. Okay, all right, so these are, so as you can see, all of them having negative sign because combustion is known to be exothermic reaction. Okay, all right, so how do we write the thermochemical equation the thermochemical equation for combustion of liquid benzene? Okay, all right, so the tip is to start from the substance itself. But this time around, formation pun kita start from the substance, which the substance is the product. Kebetulan substance dia adalah product. But for combustion, the substance is the reactant. Okay, so we're going to start from the substance that need to be burned. So this is the substance. So it is benzene. So the state is in liquid state. Okay, so combustion we requires oxygen in gas state. Okay, and then producing. So since we have carbon and oxygen and hydrogen only, that means normally it will produce CO2 in gas state plus H2O. Okay. Okay, ini sebenarnya we need to have sebelah dia on the side, we should have the enthalpy change of combustion. Okay, all right. So for this one, you don't have to consider the reactant need to be in its constituent element. Tak payah, tak perlu. Okay, because it did not, we don't have that specified in the definition. Dalam definition of combustion, we don't have to make sure that the reactant need to be in its constituent element. Tak perlu. Okay, cuma dia mesti 1 mole for the substance that need to be burned. Itu sahaja. Alright, and then the rest are all the same lah. And then you balance it. Okay, you balance the equation. So make sure that this one must maintain 1 mole. Okay, C6. So on the product side, we have only 1 carbon. That means we have to add in 6 carbon lah. Okay, and then hydrogen, we have 6 hydrogen on the left-hand side. And then on the product side, we only have 2. That means we have to add in 3, coefficient 3 there. And lastly, then only we settle for oxygen. Okay, so settle for oxygen last. Don't balance for oxygen first. Okay, because oxygen can be varies. And then after all, it is mentioned here that the substance is burned in an excess oxygen. Okay, all right, so buat oxygen tu last kali. So how many oxygen do we have in the on the product side? And on the product side, so we have here, we have 3, and then here we have 12. 6 times 2 is 12. 12 plus 3 is 15. Okay, so we have 15 on the product side. All right, so to make sure that we have 15 on both sides, so we have to use 15 plus over 2. Okay, so this is a fraction because this one and this can be cancelled out. So we have both coefficient on the reactant and product side are the same. Okay, alright. So that is how you prepare ataupun write the thermochemical equation for combustion of liquid benzene. Okay, alright guys. Try to do this checkpoint. Okay, I give you 2 minutes for you to complete this checkpoint. Okay, do it now. All right, so let's go. Okay, let's discuss the answer. So aluminium, you have to write the thermochemical equation to represent the standard enthalpies of combustion for the following substances. So we're going to start with A first, so aluminium. Okay, so aluminium, when it is burned in complete combustion, okay, in excess oxygen, O2 in gas, producing Al2O3, aluminum oxide. Okay, all right. So we have to make sure that the mole of the substance burned is 1 mole. Okay, then the rest we can alter lah. Okay, to make sure that it is balanced. So okay, this is solid. Okay, make sure that you include the state and don't forget the enthalpy change of combustion, negative 835 kilojoule per mole. Again, this kilojoule per mole, because we have specified here that it should be enthalpy of combustion, then this mole is actually referring to this substance. Okay, if dia tak specify, dia buat macam ni, enthalpy change negative 835 kilojoule sahaja pun tak salah. You should know that this is for 1 mole of aluminium, and this is also for kj, this is for, okay, belum balance lagi okay, jom balance. O2, okay, O2, so we have aluminium here 1, so here we have 2. Mana nak maintain this one? Kita kena stick to 1 on the reactant side. So here we shall use the half as the coefficient. Okay, alright, so bila kita guna half, then kita akan dapat 1 lah, which is the same as the reactant. And then how about oxygen? So we got 2/3 there. Okay, 2/3. So here we already have 2 dekat situ. Okay, here we already have 2 dekat situ. So kita kena make sure that dia kena sekejap. Kat sini 2/3 kan. Kalau kita letak 2/3 kat sini, dia tak sama. Betul tak? Dia akan jadi dapat 4/3. So dia tak balance. Sini kita 2/3. So to make sure that it is balanced, so here we shall put 4. Sorry. Kita nak 3/2 guys. We want it to be 3/2. Okay, 3/2. So we want it to be 3/2. That means here kita kena, okay, cuba kalau kita letak 3/2. Okay, sebab normally kita just simply letakkan place in the coefficient. But this one you kena be careful because if you add in 3/2 as a coefficient, bila you cancel this one, you akan dapat sini 3. But what we want is 3/2. Okay, sebab kita tak boleh usik this one. Okay, so macam mana nak dapatkan dia 3/2 there? So here kita kena make sure that it is 4. Okay, sebab bila kita 3/4, when this one cancel out, bukan cancel out, kita simplify. Okay, so this one kita dapat 2. And it is the same on the product side. Okay, so the answer should be 3/4. Okay, tak apa, buat dulu, kita try. So untuk kita terus tahu straightforward tu, kita maybe kita tak rasa terror tu kan. Tapi kalau yang biasa-biasa, so that is how we do it. 3/4. Okay, alright, so 3/4. Okay, like I said just now, if the C is not included, that means the question can the energy release can also represent for 1 mole. Okay, this can also represent for 3/4 mole of oxygen, and it can also represent -835 kilojoule per half mole of Al2O3. Okay, sebab dia in the same equation. So you sendiri yang kena tahu. Okay. So ini dah specify kan, obviously dah specify combustion. Maksudnya by definition this is for aluminium, the substance that need to be combusted. Okay, alright, so how about B? B lebih kurang lah. Okay, let's look at the answer here. So this is the answer. Okay, make sure that you get it correct for all of the coefficient especially. Okay, because this one should be maintained 1 mole. Don't forget this one. Okay, then only it is called Thermochemical Equation. Okay, alright, any questions so far guys? Ada soalan tak?
No, madam.
Ada. So far so good.
Okay, alright. So far so good, okay? Alright, so let's move on to the last standard enthalpy of neutralization in our syllabus, okay? Alright, so which is the neutralization. So to denote this standard enthalpy of the neutralization, we use N, okay? Enthalpy change, standard enthalpy change, and then we use N, small letter N. Okay, so N stands for neutralization. Okay, by definition, this enthalpy change is when 1 mole of H plus, which is in aqueous state, ion, okay, reacts with 1 mole of OH ion to form 1 mole of water. Okay, so this would be our highlight lah. Okay, if we got 1 mole of water, then definitely we have 1 mole of H plus and 1 mole of OH minus. Then only we manage to get 1 mole of water. Kalau ini tak 1 mole, then definitely H plus dengan OH minus will also not be 1.
Hi.
Madam,
Acid
hello.
and base. Okay?
Madam, tadi lag.
Tadi lag sebab saya ada dapat call tu yang saya diam. Okay, sekarang okay
Okay.
Okay. Alright. So neutralization is a reaction between base and acid and base. Okay. Alright. So when these two reacts, and neutralize one another, it will produce one of the product form will be H2O lah. Okay, so one of the byproduct form is H2O. Alright, so we have to make sure our target now, our focus now is to make sure that H2O must be in 1 mole. That is all. Yang lain tu balance lah macam biasa. The rest kita tak kisah except for H2O. Okay, alright. So sodium hydroxide, HCl, don't forget the state. Okay guys, okay, HCl and ACl producing NaCl and H2O. So turn out semua pun 1 mole. So this is not a problem lah because kebetulan semua pun kita dapat 1-to-1 ratio. So this is the amount of heat release. Okay, and the moment we saw nitrogen, so understood that this enthalpy is focusing on the to produce the H2O, the neutralization, and it produced 1 mole of H2O. Okay, what if when it involve 1-to-2 ratio of acid and base? Okay, macam mana? Memang you kena make sure that the H2O must be in 1 mole. Okay, you kena make sure of that. But what is the how do we balance easily? Okay, sebab kalau kita kena maintain satu tu to fix value, then the rest mungkin kita akan kena pakai, most likely we need to use fraction. Macam yang case tadi kan, we need to use fraction. Okay, sebab dekat sini ada banyak sangat compound yang terlibat dekat situ. Okay, so it can be complicated lah dekat situ. Alright, so my suggestion, I would suggest you to first balance the equation normally. Okay, you balance secara normal macam biasa, you nak balancekan kiri kanan. So most likely you akan dapat a value here atau which is not equal to 1. For example kan, this is 1-to-2 ratio. So kalau normally kita balancekan this one, okay, kita akan dapat CaOH2 tu tak in aqueous state plus 2 mole of HNO3. Okay, producing CaNO3 aqueous, producing 2 mole of H2O. This is how we normally balance equation, betul tak? Kita tak pakai pecahan. Okay, alright. So you go for this one first. You go for this one dulu. Okay, and then you nampak, okay, this is neutralization kan, so the H2O must be in 1 mole. So what you do is, you divide by value yang ada dekat H2O tu. Because our focus is on the H2O. Betul tak? So divide by 2 lah. So ni pun divide by 2. This one you divide by 2. This one, 1 divide by 2. Okay, alright, so you akan dapat setengah. This one is equal to 1. This one, this one is also equal to 1. See? Senang. Okay, daripada you nak come out dengan pecahan and then you kena check for nitrogen, for oxygen, for calcium, for each one of the atom present in the balance equation. So leceh lah. Macam tadi pun, you boleh juga pakai style yang macam saya cakap ni. You balance macam biasa dulu and then you divide by the value yang kita punya fokus tu. Combustion for the substance yang nak bakar tu kan. Formation untuk produk tu. Tapi normally untuk formation and combustion, I would say easier lah. Dia punya balance equation is not that complicated. So kita boleh terus balance pakai pecahan. Okay, for this one dia jadi banyak sangat yang kita takut kita miss out something. Okay, so buat cara biasa and then divide. Okay, alright. So sama juga for this one. The third one ni is 1-to-1 ratio. So it's not a problem because this is we already producing the 1 mole of H2O. Okay, so this is the amount of heat release from this neutralization. Okay, all right, so try this checkpoint 5. Okay, I give you like 5 minutes lah. Try 5 minutes. In 5 minutes, lamanya 5 minutes. 1 minute. Okay, 1 minute. 5 minutes. All right. Okay, so let's go through the answer. So sulfuric acid H2SO4 and then potassium hydroxide is KOH. Okay, so we have one OH and then here we have two hydrogen. So this is 1:2 ratio. Okay, so the ratio is 1:2. Maksudnya you kena buat macam tadi lah yang calcium just now. Alright, so this is your thermochemical equation for the enthalpy of neutralization. Okay, nampak tak macam ni kan, dia tak specify. Patutnya kena ada lah the N. Okay, you should have N because we are talking about neutralization kan. So now kita tengah cakap pasal neutralization. So by right dia kena letak N. Tapi kalau tak letak N pun tak salah. You sendiri kena tahulah. Okay, bila dia letak kJ per mole dekat sini and then this is an acid-base reaction. So for enthalpy of neutralization, it should be for 1 mole of H2O produced. Dia tak letak mole kat sini pun tak apa, dia letak kJ pun tak salah. Okay, you kena sendiri tahu, oh it can also be kJ per mole because it is producing 1 mole of H2O. Okay, but other than that, dia juga represent this half of K2SO4, 1 mole of KOH, and also half mole of H2SO4. Okay, all right, moving on. Done. Okay, so we have 3 of standard enthalpy change, formation, combustion, and also neutralization. Okay, so make sure you know how to write the thermochemical equation for each one of the enthalpy change just now. Okay, all right, moving on, we have stoichiometry of thermochemical equation. So I have mentioned about this so many times. Okay, when you alter the equation, the enthalpy change will be altered as well, because that enthalpy change represent that specific balance equation, that equation lah, that reaction. So any of the coefficient, the state or whatsoever is changed, that means the enthalpy change will also berubah. Okay, so a thermochemical equation is a balance equation that includes the enthalpy change of the reaction. Ni saya dah cakap awal dah. Okay, the value of delta H in the thermochemical equation depends on the stoichiometry of the equation and the direction of reaction, whether it is forward or reverse direction. Okay, if you change any of the stoichiometry part, the coefficient, that means the enthalpy will also change. If you reverse the reaction, that means the enthalpy change will also change. Okay, so usik dekat equation, dekat reaction, that means enthalpy pun you kena usik juga. Alright, example, when a reaction is multiplied by a certain factor, enthalpy change is also multiplied by that factor. Okay, look at equation 1. So this is equation 1. Okay, so this is a combustion reaction. And also, okay, nampak very interesting benda ni. Ini kalau kalau kita kena identify the type of reaction for this one, the type of enthalpy change for this one, it is combustion. Betul tak? Kita boleh nampak because they produce oxygen. And can it be formation too, guys?
Yes.
See? Dia boleh overlap. Okay? So siapa yang decide benda tu? You tengok and then you identify. Dia tak semestinya semua benda nak kena bagi tahu. Okay? Alright, so turn out this one is combustion, enthalpy of combustion and also enthalpy of formation. Sebab dia obeys, dia comply with the two definition. Okay? So, nampak? So jangan ingat nampak oksigen je combustion. Boleh juga formation sebab this one is 1 mole. And then the rest are all constituents element. So dia comply kan? So dia represent lah. Alright, okay. Now highlightkan this one. Okay, this is the first equation. So this is the amount of heat release. Dia release because of the negative sign. Okay, alright. Now, if lah we change the coefficient, we alter the coefficient instead of all. Okay, initially all of the coefficients are 1. So now we change to 2. We times or we multiply with 2, a factor of 2 for all the coefficient. But you don't forget, okay, please do not forget to multiply the enthalpy as well. Faham tak? Because this one is for 1 mole. So, kalau you nak pakai this one untuk for 2 mole, dia tak represent lah. Okay, because this is for 1 mole. So, for 2 mole, you have to multiply with 2. Then, this is the amount of heat release. Okay, all right. Another example. So, this is the equation again. Let's see. So, now you reverse the equation. Okay, CO2 earlier, we have as the product. Okay, now dia jadi reactant. And the reactant in the initial equation dah jadi product. Okay, so this is what we call reverse reaction. So what happened to the delta H? Okay, earlier dia negative sign. Since this reaction is reverse, so the sign become positive sign. Dia macam tu je lah, tapi maksudnya ada perubahan lah dekat situ. Okay? Okay, given the chemical equation below, so in the way, what we are trying to highlight here, the stoichiometry part dekat situ. Because we have the enthalpy change kan. Normally kita hanya balance equation sahaja. But now since we have this as our enthalpy change, the heat involved, okay, so kita kena include lah the relationship. So 1 mole of graphite will release 393.5 kilojoule of heat. So that is also relationship. Okay, all right, moving on. Okay, let's look at the example. So this is the equation, okay, and then this is the amount of heat release. Nampak tak dia bagi kJ? Problem ke kJ ni? Tak problem pun. Okay, maksudnya it is understood. kJ, or if we are referring to H2SO4, that means kJ per 1 mole of H2SO4. Boleh juga nak buat kJ per mole of H2O sebab kebetulan semuanya 1 mole. Okay, so sebenarnya kat sini kita boleh letak kJ per mole because all the coefficient are 1 mole. kJ per mole of SO3, kJ per mole of H2O, kJ per mole of H2SO4. Okay, so bila kita letak kJ saja, it's like the general description of the energy for the reaction. Okay, bila dia dah cakap mole tu, kJ per mole maksudnya dia dah specific. Mole tu is referring to what? Because this is normal equation. Dia bukan combustion, dia bukan neutralization, and it is not formation. Okay, so dia adalah equation. So kita nak represent mana? Tak ada nak represent mana pun, kita pakai kJ because kita punya understanding tadi macam yang saya cakap tadi. Per mole of whatever that we have in the equation. Okay? Alright, A. Calculate the enthalpy change when 0.05 mole of SO3 dissolve in water. Okay, from the equation, let's use other color, boring. Okay, from the equation, 1 mole of SO3 release this amount of energy. So the question is asking for 0.05 mole of SO3. So how much of energy is released? How much of heat ataupun what is the enthalpy change now? Okay, alright. So kita pun start lah from, so this is A, okay. The information given. Okay, so this is the conversion factor. So down here we should have mole SO3. Alright, so the conversion factor we can obtain from the balance equation. So 1 mole of SO3 will produce, okay, will release 56.5 kilojoule of heat. Okay, alright, so you can solve for this one and then you akan dapat lah the kg. Don't forget the sign. Alright, so B, how about B? Calculate the enthalpy change when 24.5 gram of H2SO4 is produced. Okay, so first step is you convert 24.5 gram into mole because this is in gram. And then you relate. Okay, from the equation, 1 mole of H2SO4 is produced when N release 56.5 kilojoule. So that is the relationship kan. Okay, so you masuklah dalam equation. You buatlah calculation. Okay, so 24.5 gram. So this is the step where we convert into mole. So down here we should have H2SO4. So berapa dia punya ni? It is 80, is it? No, 98. The molar mass is 98. So up here we have 1 mole of H2SO4. So this 1 gram can be cancelled out. So we have it in mole already. So now is the time to relate with the enthalpy change from the balance equation. So down here we should have mole of H2SO4. So 1 mole of H2SO4 will release 56.5 kilojoule. Cancel. Okay, so we have in kilojoule. Don't forget again the negative sign. That's the tekan calculator je lah, apa lagi. Okay, alright, how about C? Okay, how about C? Calculate the mass of SO3 needed to generate 100 kilojoule of heat. Okay, so dia bagi heat pula, dia nak tahu the mass of SO3. Okay, look at the balance equation. Okay, alright. So for to produce, okay, to generate 56.5 kilojoule, it requires 1 mole of SO3. 1 mole of SO3 is equal to berapa gram lah, depends on the molar mass. Okay, so to generate 56.5 kilojoule requires 1 mole. So kalau you ada 100 kilojoule, berapa mole of SO3? Berapa mole of SO3? And then you convert into gram. Okay, alright. So you're going to start from the information given. Kilojoule. Don't forget the negative, guys. Don't forget the negative sign because dia kata generate, maksudnya release. Okay, so negative 100 kilojoule and then conversion factor from the balance equation. So down here should be in kilojoule. So 56.5. So now we are talking about SO3 kan. So from balance equation, 1 mole of SO3. Okay, so don't stop here. You have to extend further in order to find the mass. So down here we should be in mole of SO3. Okay, all right, 1 mole of SO3, the molar mass is 80 gram. Okay, 80 gram. Okay, cancel, kj, cancel with kj, and then we have in gram. Gram lah. SO3. Nampak tak? So, stoichiometry je lah. Stoichiometry. Tak ada benda yang baru. Dia yang barunya ada heat saja, ada enthalpy change. That is all. Stoichiometry is still the same stoichiometry that we have learned during our school time. Okay? Sama je. Okay, kalau you pakai conventional method, make sure that you include the unit again. Okay? Unit. Okay, maybe you can try out checkpoint 6. Cuba buat checkpoint 6, guys. Checkpoint 6 and 7. Okay, cuba buat checkpoint 6 and 7. I give you like 3 to 4 minutes macam tu. Okay. Okay, complete checkpoint 6 first. Okay, checkpoint 7 is little bit tricky. Okay, tricky as in we have both mole for hydrogen and nitrogen. Dia bagi dua-dua mole guys tu. Normally, did you guys notice? Okay, so far dia mesti dia just bagi one information saja for one of the reactant ke or product. Dia hanya bagi satu information saja macam ni kan. 0.483 of graphite. Earlier on for this one, okay, dia bagi for SO3 only. For B, for H2SO4. And then for C, dia bagi the heat. But this one, this time around, dia bagi 2 mole dekat situ. Okay, we have 2 informations there. So what need to be done, okay, in order to find the enthalpy change? How do we consider this? Should we go for one of them only ataupun macam mana? Okay. Siapa yang tahu boleh buat lah. Siapa yang terkebil-kebil boleh fikir-fikirkan lah. Okay. Yeah, are you done with checkpoint 6 kan? Guys?
Yes.
Yes.
Okay.
Okay, maybe we can go through the checkpoint 6 first. Okay, the standard enthalpy of combustion for graphite is this. Okay, A, write a thermochemical equation for the combustion of graphite. Okay, A, graphite is carbon. Okay, so it is in solid and you must write there graphite. Wajib. And then combustion of graphite. Okay, so you must have oxygen lah. And then producing CO2 in gas state, and don't forget the delta H of combustion because the question specifically mentioned the standard enthalpy of combustion. That means you have to include the C. Okay? Tak include pun include lah, senang cerita. Saya bagi yang kasih confirm punya lah. 5 kilojoule per mole of the substance being burned. In this case, graphite. Okay, do we need to balance? It's already balanced. Kita check lah, check. Okay, carbon, okay, 1 mole. Oxygen is also 2. We have 2 oxygen on both sides. So it's already balanced. Okay, all right, B. Calculate the heat evolved when a 0.483 gram of graphite is burned. Right, okay, so you need this equation, okay? In order to calculate this, you want to relate the graphite and the energy release, okay, you need to have an equation. So the stoichiometry part is normally obtained from the equation. So without the equation, how can you solve for B? Okay, so we're going to start from... So from this equation, okay, 1 mole of graphite will release negative 393.5 kilojoule. So you ada 0.483 gram of graphite. So how much energy will be released? How much heat will be evolved ataupun given off? Okay, alright. So we're gonna start from the gram given. Carbon, okay, carbon. Ain't got time to write graphite or whatsoever, okay. Minimize masa maximizekan masa anda tu. Cepat. Maximize masa. Okay, tak apa. Gram carbon. Okay, so this is the part where we convert into mole. So here gram carbon. So down here should be also gram carbon. So it is 12 gram carbon. Is also equal to 1 mole of carbon. Okay, and then proceed further. So this is the part where you relate with the heat given. So down here should be in mole carbon. From equation, 1 mole of carbon will release this amount of heat. Don't forget the sign, guys. 0.5 kilojoule. Okay, that is all kan? Nak tanya heat evolve kan? So, apalah, itu je ke? Boring lah. Okay. Right. So this is the answer. It's negative 15.9 kilojoule. Okay, all right. Checkpoint 7. Okay, the following chemical equation represent the reaction in Haber process. So given is the equation involved. Calculate the enthalpy change when 0.25 mole of H2, which is this one, and 0.25 mole of nitrogen. As you can see, both mole are given and they have the same mole. Even though mole dia sama, but of course the mass will not be the same, betul tak? Nah, mole dia sama, mass tak sama. And then after all, from the equation, it is not 1-to-1 ratio. Kan? So jangan ingat mole yang sama, so mass dia sama, and then the rest all will be sama. Okay, tak boleh lah, dia mana boleh sama. Mole ni because you find the ratio of mass over molar mass, baru you dapat mole yang sama. Okay, tapi to begin with, the molar mass is also not the same. Kan? So the molar mass is also not the same. So you jangan simply nampak mole dia sama terus mass dia sama. Kan Okay. Okay. In this case, we have to consider the limiting reactant. Okay. Sebab dia nak tanya enthalpy change dekat situ. Berapa banyak yang heat release if we react these two together. So we have to consider whether any of these two is the limiting reactant, because kalau salah satu tu adalah limiting reactant, of course the reaction will stop kan, sebab limiting reactant dah habis. Okay, alright, so it depends on the limiting reactant, the amount of heat release. Okay, because the heat is also the product. Okay, dia release heat kan. So kalau ikutkan heat, tambah heat, one of the product. So the amount of heat release depends on the limiting reactant. So we have to check whether hydrogen ataupun nitrogen is the limiting reactant. Okay, alright. So misi dia macam lah kita cari limiting reactant lah. Okay, so we're gonna start with carilah nitrogen dulu lah. Saya start dengan nitrogen sebab dah tertulis N. So 0.250 mole of nitrogen. Okay, from the equation, 1 mole of nitrogen will release, okay, sebab heat kan? Heat is one of the product. You can also use NH3, boleh, it's not a problem, because you will still get the same limiting reactant. Okay, janganlah ingat you pakai NH3, you pakai heat, nanti dia produce different limiting reactant. Mana boleh, dia kan daripada balance equation yang sama. So they should have the same limiting reactant. Okay, alright, so for this time, saya nak pakai heat. Okay, dia punya comparison of product. So you have to compare which one will produce least amount of product. Okay, so 92.2 kilojoule. Okay, tolong calculatekan what will be the value for this one. Berapa?
Negative 23.05.
23.05. Okay, alright. So this one also from the balance equation, this one should be mole H2. Okay, so we have 3 mole of H2 will release 92.2 kilojoule. Okay, so what's the value for this? Apa?
Negative 7.68.
7.68 kilojoule. Okay. Alright. So, untuk kelas S13 dengan S14 saya guna NH3. Untuk kelas awak saya guna heat ni. Okay. Tapi you should get, kita sepatutnya dapat the same limiting reactant. Okay. So then we can compare, okay, which of these two produce the least amount of heat. Okay, so produce the least amount of heat ataupun produce the least amount of product. Therefore, hydrogen will be completely used up. First, dia akan dia habis dulu. Okay, therefore, hydrogen is the limiting reactant. Kalau you dah tahu hydrogen is the limiting reactant, that means nak jawab soalan ni, enthalpy change, you akan gunakan the mole of H2. Okay, alright. So you mungkin akan cakap, alah madam kan mole dia sama kan? Memanglah sama. Okay, dia tak sama dekat sini Okay, you akan pakai mole of H2. Kenapa pakai H2? Kenapa tak pakai N2? Okay. Okay, azan. Sekejap ya. Okay. Baik. Tadi kan you may wonder, alah madam, both of them pun 0.25 kan? Okay, dia akan varies dekat sini. Memanglah sama. Okay, starting will be the same, but you want to calculate the jom calculate dulu. Okay, so from the equation, okay, the enthalpy change kan, mole, mole. Mole H2. From the equation, we require 3 mole of H2 to release 92.2 kilojoule. So the answer will be mole cancel. Kita kena buat apa? 7.68. Betul tak? Sama lah. Memanglah sama. Tapi kalau dia tanya mass kat sini, of course lah mass dia akan lain kan. Dia kalau dia tanya katalah mass of NH3 ke from the amount of heat given, okay, so dekat situ it will involve the molar mass involved will be different dekat situ. Okay, so bila different, that means you punya final answer will also be different. So cuma kita nak tahulah kat sini you mesti specify. Okay, kalau dalam exam lah, okay, kita nak, sebab after all dia punya mole dia sama kan kat situ kan. Kita nak tengok you pakai 0.25 mole of nitrogen ke you pakai 0.25 mole of hydrogen. Sebab dia sama kan. So kalau you letak sini nitrogen, salah lah. Because you are not considering for the limiting reactant. So you mesti tulis kat situ hydrogen. Wajib tulis hydrogen. Okay. Okay, salah. Bukan. Saya nak cakap ni. Kalau you pakai nitrogen, if this is for you katakanlah sebab you kata mole dia sama kan. This is nitrogen. Then what will happen here? This one will be different. Itulah madam ni. Loss tadi Kalau you are using nitrogen, the difference will be here. Okay, from the equation, 1 mole of nitrogen is used to produce 92.2 kilojoule. So of course jawapan you akan lain. Betul tak? Sebab kita akan tengok, okay, kadang-kadang student tak letak pun this one. Dia pakai mole je guys tu. Okay, kita macam, ini mole nitrogen ke mole hydrogen? Maklumlah sama kan? Kita tengok dekat sini. If you are using 1 mole, that means you are referring to nitrogen. Kalau if you are using 3 mole, that means you are referring to hydrogen. Okay, so kat sini lah berbeza sebab from the balance equation, they do not have the same coefficient. Therefore, by right, they will produce different amount of product. Okay, jangan ingat dalam thermochemistry tak ada limiting reactor. Kan saya kata, macam mana you nak tahu dia akan tanya limiting reactant ke atau tak? Ada possibility to apply limiting reactant. Kalau dia bagi info for both. Maksudnya you can find out the mole for both. Then most likely you have to consider for limiting reactant. You kena check for both. Mana yang produce the least amount of product. In this case, the least amount of heat. Okay? Alright, moving on. So, any questions so far related to the stoichiometry of the enthalpy change before we proceed to calorimetry?
No, madam. Okay.
Okay, alright. How about others? Then we have only one feedback so far. Okay, how about others?
Okay, madam.
Okay, madam.
Okay, alright, sedap je dengar okay tu. Bagus, alhamdulillah. Okay, now let's move on to calorimetry. So calorimetry is what I consider the most famous question. It's like 98% will be coming out in the exam. Okay, calorimetry 90% of this subtopic will be coming out in the exam. Dia macam limiting reactant last time. Okay, confirm keluar exam. Same goes to calorimetry. Okay, right. As you can see, we have a lot of learning objective for this subtopic alone. So please make sure that you really understand the concept. Okay, right. So make sure you cover lah all of these LOs at the end of this subtopic. Okay, moving on. So some of the term that used in this calorimetry punya subtopic, you have been introduced to it. Dalam fizik, masa you punya SPM, okay, you are already familiar to this term. So kita just like macam recap, okay, kita by right kita go through very briefly je lah. Tapi awak tahulah saya kan, briefly saya tu, dia 2 kali ganda, briefly orang lain. Okay, heat capacity and specific heat capacity, okay. Heat capacity, or we can represent it as capital C, is the amount of heat required to raise the temperature of a substance by 1 degree Celsius. Energy ataupun heat yang diperlukan, haba yang diperlukan untuk menaikkan temperature, suhu sebanyak 1 degree Celsius. Berapa banyak energi yang diperlukan untuk nak naikkan 1 degree Celsius. Okay, alright. So the heat is directly proportional to the T, to the temperature. So when the temperature increases, right, the heat also increases. Ataupun when the heat increases, the T will also increase. Okay, alright. So to make to solve this relationship, okay, we have this equation. So Q is equal to constant times delta T. So constant, kalau kita nak find out the constant, so this constant is what we call heat capacity, guys. Okay, selagi kita menggunakan barang yang sama, temperature tu kita tak berubah, so the heat capacity will be the same. Contohnya, if you are using calorimeter, okay, you are conducting experiment in the same calorimeter. So the heat capacity of that calorimeter will be the same lah throughout the experiment. Okay, so that is what we call heat capacity. So to find heat capacity, we can simply divide Q over T. So this is the unit lah. Okay, so because Q is J and then the delta T is still temperature. You may use degree Celsius ataupun K negative. You may use degree Celsius or Kelvin. Because of kenapa boleh dua-dua boleh pakai? Because dia adalah change in temperature. Kalau dia temperature saja, you kena pakai salah satu. Okay, depends on dia specify apalah. You tak boleh pakai sebab the value will be different. But this one, the value it should be the same because we are using the change in T. Okay, the change in temperature, not the temperature itself. Kalau Kelvin sahaja, of course it will give different capacity value. If you are using degree Celsius alone, okay, it will be different as well. Okay, and then, tapi ni delta T delta T, okay. Specific heat capacity, on the other hand, is the amount of heat required because the term specific there is added into the heat capacity. So become specific heat capacity. So to represent specific heat capacity, we use C in chemistry lah. Okay, in chemistry, in our syllabus, we use CS, small letter S. Okay, it's the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay, they become more specific dekat situ. This is for 1 gram. Berapakah the energy yang diperlukan untuk menaikkan suhu sebanyak 1 degree Celsius untuk 1 gram substance? See, they become more specific. Alright, so to calculate this, to calculate the Q, the heat involved, we're going to be using this formula MCS delta T. Okay, to find out the CS, okay, kita boleh transfer the rest to the other side. So this is how you can solve for CS. Okay, alright. If you want to determine the unit for CS, senang saja. Q will be J, M will be G, delta T will be degree Celsius or Kelvin. Okay, if you simplify this, you naikkan semua ke atas, JG negative 1 degree Celsius negative 1. It can also be in K negative 1 because again it is delta T. Okay, just to let you know, so we have QMCS delta T. Okay, when these two are combined, this is what we have. This is why this is this is C actually. Susah benar nak cakap. Okay, this is C actually. C delta T. Because M times CS is equal to C, the heat capacity. Again, example calorimeter. Okay, if you are using the same calorimeter, kalau you pakai this formula, okay, this formula, you kena tahu the mass of the calorimeter and then you kena tahu the specific heat calorimeter and then every time you nak pakai, takkanlah kita nak kena darab. Dan after all, it's still, dia akan remain constant because you are using the same calorimeter. Betul tak? So, might as well make this a constant. So, the constant is heat capacity. The heat capacity of that substance. Okay, which is the M, with reference to the M, So of course, calorimeter has its own mass kan. So kita, when we time these two, we multiply these two, this is what we call heat capacity for that mass. Okay, alright. So kalau CS tadi, kita kena consider for 1 gram. For 1 gram Okay, so macam mana nak baca JG per gram ni? Yang ni statement dia cakap ni. Heat yang diperlukan untuk menaikkan suhu sebanyak 1 degree Celsius untuk 1 gram of substance. So, kalau you ada 1 gram, kalau you ada 100 gram, kalau you ada 20 gram, macam biasalah, okay? Calculation tu. Alright, factors that affect heat capacity on heat capacity of an object. Okay, so you have to consider the mass, like I said. The mass will also affect the heat capacity. Okay, so the larger the mass, by right, the larger the heat capacity. Contohnya bilik kuliah 60 orang dengan bilik kuliah 200 orang. Okay, yang mana yang boleh accommodate lebih banyak student? Bilik kuliah 200 orang lah. Okay, so the larger the mass, that's why the larger the mass of the matter, therefore, the more heat can be absorbed. The more heat can be absorbed and therefore it takes longer time to increase the temperature by 1 degree Celsius. Okay, contohnya you ada, okay, this one dengan kecil. Okay, lama tak masa yang diperlukan untuk penuhkan kotak yang besar ni? This one, dia lebih kecil. So masa yang diambil sekejap saja. Katalah kita bagi heat kan, kita nak panaskan these 2 kotak. Okay, so masa yang diambil untuk panaskan this larger box is longer compared to nak panaskan yang kecil ni. Okay, so nak panaskan maksudnya dia absorb dulu, dulu, dah penuh baru dia naik 1 degree Celsius. Okay, and then panaskan lagi, naik lagi 1 degree Celsius. Okay, so it take longer time to fulfill lah the capacity of the heat for this larger box compared to yang kecil ni. Okay, alright. So that's why mass of matter can affect the heat capacity. So contoh, if we have 200 gram of water, by right, it requires twice as much heat to raise its temperature by 1 degree Celsius compared to 100 gram of water. Okay, because muatan dia tu, capacity dia tu. So dia ni boleh tanggung, katakanlah 50 kilojoule of heat. Dia boleh stand 50 kilojoule for heat sebelum dia naik dia punya temperature dia. This one boleh tanggung less than 50 kilojoule. Okay. So macam contoh lagi, analogi lain, stres. Awak dengan kawan awak ni dia tahan stres. Awak ni kurang tahan stres. Stress tolerance very low. Okay, maksudnya apa? Okay, kawan awak ni Stres macam mana pun dia punya ketahanan dia tu sebelum dia apa nama tu dia apa dia apa dia
Meledak.
dia meletup, nak cakap itu pun hilang okey, sebelum dia meletup tu lambat. Okey, dia boleh tahan. Okey, orang pukul dia ke apa kan, benda ke bagi homework banyak ke, dia relax je kan. Cara macam mana dia relax tu depend kat dia lah kan. Tanta dia relax dengan cara tak buat kerja. Okey, tu lantak di situ. Tapi nak cakap stress tolerance dia tu very high compared to awak, okey, yang very low. So yang mana yang akan meletup dulu kes ni? Meletup tu as in temperature yang akan naik dulu. You lah yang akan meletup dulu sebab you punya ketahanan, capacity stress you is very low. Okay, so itu maksudnya capacity. Tadi stress capacity, this one heat capacity. And then types of material, this is by nature. Okay, you mesti wonder, okay, kenapa kawan you ni dia nampak tak stress you cepat stress. Tu by nature. That is what we call by nature. Okay, so lain-lain orang, lain perangai dia. Same goes to substances. Different material will have different capacity, kebolehan, the nature of the material itself. For example, if we are comparing sand dengan water, okay, both of them have the same mass. Mass yang sama, and then kita bagi 1000 joule of heat. Heat, energy yang kita bagi pun sama. However, dia punya acceptance is different. Okay, alright, bila kita give this amount of energy to sand, dia punya temperature increase by 12 degrees Celsius. Tapi kalau kita bagi dekat water, the temperature increase, okay, by 2.4 degrees Celsius. Kebolehan water tu. Okay, so itu memang by nature dia lah. Of course kita akan kena tengok lah apa yang ada dalam water and what not. Tapi the substance itself is very, maksudnya that is the speciality of the substance. Okay, alright, so the larger the heat capacity of the object being studied, the smaller the temperature rise will be for a given amount of heat. Okay. Right, so this is the specific heat capacity, guys. This is the specific heat capacity, right? So different substance may have different specific heat capacity, kebolehan untuk dia accept the heat, okay? Before dia naik sebanyak 1 degree Celsius, temperature tu naik sebanyak 1 degree Celsius. Tengok siapa yang paling tinggi, water. The rest macam metal kan, metal, no wonder lah metal cepat panas sebab dia punya heat capacity is very low. Okay, dia very low. Water on the other hand is quite high lah compared to the others. Okay, so dia perlukan this amount of heat for 1 gram of water to increase the temperature by 1 degree Celsius. Make sure you pandai baca unit ya. Okay, apa maksud ni? Apa maksud ini? And then you must be able to make comparison. Jangan based on value compare macam tu. You kena make sure that you know, you understand the unit. Okay, so you kan dah nak belajar advance ni, you tak boleh dah memorize macam tu. It won't bring you anywhere. Okay, okay. Determine the heat capacity of solid. And 800 gram of aluminium block has a specific heat capacity CS of this. This is specific heat capacity. The moment you nampak ada gram, automatic. This would be specific heat capacity. Calculate the heat capacity of the aluminium block. Okay, alright. So like I mentioned to you just now, you can calculate the C of the aluminium block. I mean the heat capacity lah. Okay, because we start out dengan macam ni, MCS delta T. So this MCS is equal to C delta T. For something yang memang permanently macam itu. Okay, alright. Tapi kita boleh jugalah calculate macam ni given the mass. So kita boleh time lah. Okay, don't forget the unit here. Okay, you are calculating for heat capacity. So G cancel. You have J and degree Celsius. So this is the heat capacity. Okay, right. Another example. A piece of silver. has a mass of 362 gram with heat capacity of this. Determine the specific heat capacity. Alamak, dia main-main pusing-pusing macam tu lah. Okay, dia main-main pusing-pusing macam tu. Kalau saya suka pegang satu formula saja. So this one is equal to C. Okay, alright. So kalau C is equal to sama. Okay, alright. So you want to find this one. So C over M. Don't forget the unit again. Okay, so this one they combine semula. G -1, C -1. Okay. Another example. The quantity heat from a temperature change. Okay, so 250 gram of water was heated, dipanaskan, and the temperature raised from 25 degrees Celsius to 30 degrees Celsius. Okay, all right. So let's just determine the type of reaction for water ataupun the process of water absorbing the heat. This is an endothermic process. You kena determine that one first, because later bila you calculate for heat, it's either negative ataupun positif. Kalau dia adalah endothermic process, tapi dalam calculation you dapat negatif, itu salah lah tu. Macam mana boleh dapat negatif sedangkan the process is endothermic? Okay, that's why you punya, once you determine it is endothermic, then you punya mathematically you should supporting the endothermic process. Yang ni kita kata dia endothermic. Kenapa? Sebab you panaskan the burner, okay, you heat up the water in a pot, katakanlah dekat dalam pot. So water tu akan absorb the heat kan? They absorb the heat from the burner. Okay, they absorb. So what happened to the water punya temperature? The temperature of the water, since they absorb the heat, so they akan increase. So from 25 to 30 degrees Celsius. Okay, so that is an endothermic process. Because for the water lah, for the burner ni dia adalah pemanas tu, dia adalah exothermic. So you patutnya dapat positive value here. Okay. Alright, so again, G cancel, C cancel, and then you are left with J, and then you convert into KJ. Okay, bolehlah try lah buat checkpoint 8 ni. Senang sangat, tak apa. Try buat. Saya bagi 2 minit. 2 minit. Okey, jom. Tak boleh lama-lama sebab saya target sampai calorimeter calorimeter. Okay, checkpoint 8, 6.22 kilogram. Okay, nampak kat sini kilogram. And then degree Celsius, calculate the specific heat capacity of copper. So normally for the specific heat capacity, we will go for gram. Tapi tak salah sebenarnya in kilogram. Okay, tapi normally memang by definition it should be for 1 gram, betul tak? But it can be changed. Tapi by definition, it's supposed to be 1 gram. So by right, this one you kena change into gram. Okay, all right, so you're going to be using the same equation, Q is equal to MC S delta T. Okay, let's just go through. Dia endo ke exo ni? A 6.22 kilogram of copper metal was heated, dipanaskan from this temperature to 300 temperature. So, dipanaskan. So, the metal absorb the heat. Therefore, metal is endothermic and the surrounding will be exothermic. So, you should get, kalau you are required to calculate the Q, that means you kena dapat positive value lah. Okay, but this one you have to calculate the specific heat capacity, this one. Okay, so your value should be G -1, C -1, J, G -1, C -1. This one, okay? All right, then we have another checkpoint here. This is pun more or less the same as the previous checkpoint. Cuba saya suka nak tengok, is it endo or is it exo? Okay, calculate the heat release in kilojoule for this amount of ethylene glycol in car radiator cools from 37 to 25 degrees Celsius. Okay, dia menyejuk. Macam mana cara dia menyejuk? Dengan cara dia release heat. Okay, dia release heat. So dia panas. So nak cara dia jadi sejuk, dia kena remove the heat. So bila dia remove the heat, the energy become less. So that's why the temperature now decrease from 37 to 25 degrees Celsius. And is it endo or exo? The answer will be exo. Sebab dia release the heat. Okay, release the heat will be exo lah. So your final answer should be, the final value for the heat should be Q, negative Q. Okay, negative value. Right? Okay, this one. Okay guys, jom calorimeter. Ini yang wajib ya. Ini yang agak critical for calorimetry. Okay, what is calorimeter? Calorimeter is a device used to measure the amount of heat released or absorbed during chemical reaction. Okay, so we can conduct experiment. If let's say we want to conduct an experiment and we want to collect the to collect ataupun to retain the heat. Katakanlah the experiment, the reaction release heat and we want to retain the heat. How can we do that? Kalau kita setakat pakai beaker, of course, beaker, okay, of course the heat will be released to the surrounding. Okay, so how do we retain that heat? So one of the ways by using calorimeter, okay, so that the heat can be retained. So we can study the amount of heat released or absorbed during chemical reaction. So chemical reactions are accompanied by the release or absorption of heat. Therefore, the calorimeter is designed to minimize heat loss from reaction to the surrounding. So apa purpose of using calorimeter ni? Why do we need to use calorimeter instead of beaker? Because of the ability of the calorimeter to retain the heat. Maksudnya dia punya insulation dekat situ. Okay, dia boleh minimize the heat loss. We do not want the heat to be lost to the surrounding. So kita kena ada barrier dekat situ. So that calorimeter behave as a barrier there. Okay, dia contain the heat. So they minimize the heat loss to the surrounding. Okay, right. So the calorimeter is nearly an isolated system. That means the system will not be released to the surrounding ataupun the Q will not be released to the surrounding. So the amount of heat release will be zero. Okay, the amount of heat yang hilang will be zero if you are using calorimeter lah ataupun almost equal to zero. Ada pun mungkin very, very minimum. Okay, the measurement of heat change will depend on the heat capacity of the calorimeter, of course. Okay, the heat change kita kena consider because the calorimeter is also the surrounding. Okay, calorimeter adalah surrounding juga. Bila you conduct reaction in a calorimeter, so you ada when the moment the heat is released, the solution will be the one who absorb the heat, betul tak? The first surrounding yang akan directly contact with the reaction will be the solution itself. Okay, and you have the calorimeter. So that calorimeter, okay, dia pun ada its own heat capacity. So normally the heat capacity for calorimeter would be very low. So apa menunjuk apa yang kita boleh dapat daripada heat capacity of calorimeter? Kita expect it to be low. Sebab apa? Sebab dia tak absorb the heat. Bukan dia tak, dia kebolehan dia nak absorb the heat is very low. So dia punya heat will be contained in the solution. Okay, so dia depends lah juga. Ada juga calorimeter yang has higher heat capacity. So kebolehan dia nak accept the heat. You kena come back pada apa maksud heat capacity lah. Okay, the energy required to raise the temperature by 1 degree Celsius. Betul tak? And then the heat capacity of the calorimeter is the amount of heat absorbed by the calorimeter for each degree rise in temperature and is called the calorimeter constant. Okay, we have C, which is the heat capacity of the calorimeter. So this is already combined, M dengan CS. Okay, so kita just assign it as C, big C, okay, capital C of calorimeter, the constant C, because we are going to be using the same calorimeter. Unless you change to other calorimeter, then you might need to consider, you have to consider for different C value. Okay, all right. So we have two types of calorimeter. We have constant volume bomb calorimeter, and we also have constant pressure calorimeter. So constant volume, okay, the name of this calorimeter is bomb calorimeter. For constant pressure, the name is coffee cup calorimeter. Okay, so this is the easiest way to prepare this calorimeter. Okay, you just need a styrofoam cup. Okay, you need at least 2 styrofoam cup, and then you stack them together, okay, to minimize the heat loss lah. And then you have a lid, okay, cover dia ni, and then you place in the thermometer. Okay, so as simple as that. So this will be the cheapest alternative to prepare the calorimeter lah. Okay, and then bomb calorimeter ni of course lah dia yang paling mahal lah, sebab okay, dia punya insulation dia tu, this is steel bomb. Okay, the reason it is called bomb sebenarnya dia memang akan ada letupan sikit dekat situ. Okay, let me just draw this one, transfer this one. Saya boleh cerita in detail. Madam suka being extra. Tak payah cerita pun tak apa. Excited. Okay, alright. So this is one of the method that we use to determine the calorie of the food. Okay, kat you punya nasi lemak you tu, untuk 1 gram nasi lemak berapa kalori. So one of the way to determine the calories of the food is by using this bomb calorimeter lah. Kita tak tahulah currently dia punya tu cara macam mana, tapi saya terbaca, okay, cara this bomb calorimeter, the application is that, okay, dia boleh determine the calories of the food sample ataupun any sample lah. Okay, what happens is that, okay, nampak tak dia punya design dia tu. So this is metal steel tau, steel bomb. Okay, tengok dia Okay, saya terkeluar. You guys boleh dengar tak?
Boleh.
Boleh.
Dah tertinggal. Macam. Kat sini kan? You guys kat sini kan? Ke dah tertinggal jauh tadi? Tak perasan? Dekat bomb calorimeter still. Betul tak?
Yes.
Betul.
Alhamdulillah. Okay. Alright, so sambung balik. Okay, stirrer kan? Sampai stirrer tadi, betul tak? Stirrer?
Madam tadi waktu Madam explain dia memang lag.
Lag ke? Sampai mana sebenarnya awak dengar?
Steel bomb.
Steel bomb, tapi dekat mana? Saya tadi tengah explain stirrer, okay, thermometer, oxygen supply, and then stirrer. You dengar sampai dekat mana?
Nasi lemak.
Nasi lemak. Jauhnya. Aduh, ya. Okay, nasi lemak tu, okay, kita boleh determine the amount of energy released from 1 gram of nasi lemak. For example, the calories, okay. Alternative to joule, we can measure the amount of energy in calories. Boleh juga. Okay, benda yang sama, cuma different unit. Okay, so kita pun place the nasi lemak inside this bomb. Okay, alright. So dekat situ kita ada ignition wire dekat sini. Dah lock. Saya still connected ke? Nampak macam dah tak ada dah ni. Hello, hello.
Ada madam.
Ada, Madam.
Ada Oh, okay. Alright. Wah. Okay. Sambung. Pelik. Alright, so ada this ignition wire and then kita nak combust this sample. That's why we need this oxygen supply. And then we have thermometer. So in this bomb calorimeter, we have water inside here. Okay, bila dia burn nanti dia akan release the energy and then the water will be accepting the heat. Okay, alright, so thermometer is to record the temperature and stirrer is to disperse the heat later on. Okay, alright, so as you can see dia ada heater dekat sini and it is fully insulated. Okay, meaning that there will be no energy loss to the surrounding. Okay, tak ada. Alright, so bila dia bakar, okay, dia ignite, okay, and then terbakar. So bila terbakar, we know that it will produce gas, betul tak? We produce gas dekat situ, gas. So bila gas ada dekat situ, it will the gas will be building up in this chamber. So tapi dia tak boleh keluar, that's why dia constant volume. Okay, they cannot go anywhere. So the gas is keep building up. Dah makin banyak. Tapi tak boleh move anywhere. Okay, dia tak boleh keluar, tak boleh apa. So that is when the small explosion occur. Boom. Macam tu. And then bila bom meletup tu, it will release the energy to the surrounding. Okay, so dia akan release the energy to the water. And then the temperature will be recorded. So there is a change in temperature. Okay, so kita pun measure lah the heat absorbed by this calorimeter. Okay, because Q system, sometimes kita tak boleh nak measure directly tau. Kita tak boleh measure directly the heat of the system itself. So one of the way is kita kena relate lah that Q system is equal to Q surrounding. Bila kita tahu Q surrounding, automatically we will know the Q system. Betul tak? So ada benda-benda yang kita tak boleh nak measure directly. So one of the way is by using this calorimeter. Kita measure the system and the surrounding lah. We measure the surrounding. Okay? So the reason it is called constant volume is because of dia punya volume tak berubah. Okay? Volume tak berubah. But this one, dia opposite lah. This one is constant pressure. Okay, kita buat dekat lab kita tu je. Tak ada ubah-ubah pressure pun. We use the normal pressure, our 180 amp pressure. Okay, alright. So this one saya nak highlightkan. If you are using bomb calorimeter, okay, the Q is also equal to the internal energy. Okay, if you are using bomb calorimeter, the Q, the heat release, will be equal to the internal energy, the change in internal energy. If you are using coffee cup calorimeter ataupun the experiment is performed at 1 ATM, that means we are calculating for enthalpy change. The Q is equal to enthalpy change. Okay, this is at constant pressure. So yang macam yang kita calculate tu, kalau kita buat at normal condition, it will be the H lah, bukan E. Kita tak buat E, kita buat H. Okay, that's why yang sebelum-sebelum ni kita calculate for H, because at normal pressure. Okay, alright, so we're going to be using this relationship. System, reaction, surrounding. So the exchange of heat kan. So if it's exothermic, so the system will be releasing the heat. So that's why dia ada negative value. Dia yang panas dekat situ. Okay, so the surrounding will be absorbing the heat release from the system. This is for exothermic. So you're going to be using this formula. If the system release the heat, this is the system release the heat. Okay, kalau endothermic, the system absorb the heat from the surrounding. Okay, alright. So you akan pakai ni lah sebab kenapa ada negatif dekat situ? Sebab this is exothermic. The system release the heat. Okay, alright. Okay, so far okay ke? Ada lagging ke? Ada lagging ke tak ada?
Tak ada.
Okay, alright. So saya jalan. Okay, types of calorimeter. Okay, ni cara nak calculate lah. Okay, so we have bomb calorimeter and coffee cup calorimeter. It depends on the question lah, of course. Okay, what type of calorimeter is given to you. Okay, so for bomb calorimeter, it will be for exothermic reaction. Because the combustion reaction normally is performed in bomb calorimeter. So combustion will be exothermic. But for coffee cup, it can be exo and it can also be endo. Okay. Alright, so like I said just now, if you are using bomb calorimeter, so we have this relationship. We calculate the Q and then we can also equate the heat release equal to delta E. But for constant pressure, for coffee cup, it is equal to delta H. This is what we call enthalpy. Okay, so whatever it is, you're going to be using this relationship. If it's isothermic, of course, this one will be negative. It's the hot one. Okay, ini dia yang release heat. That's why sini negative. You define Q system, Q surrounding. Sama juga, constant pressure, Q system, Q surrounding for exothermic reaction. And then you define, system you apa? Apa system you? Reaction itself lah. Betul tak? And then what is the surrounding now? H2O, this one pun subject to bomb calorimeter ni sebab dia ada air dekat situ kan. Okay, kadang-kadang air ni dah inklusif dalam bom tu sendiri. So depends on the information given. Okay, Q calorimeter of course. Ini kita kena consider lah because other than the water, the calorimeter also accepts the heat. Okay, sama juga for coffee cup. Sama. Q reaction, QH2O plus Q calorimeter. Okay, alright. For to calculate the Q reaction, you kembangkan lah H2O ni, mass dia berapa? CS delta T. And then Q calorimeter dia berapa? Okay, alright. So for this one, normally, okay, again it depends. Kalau coffee cup calorimeter ni, okay, sometimes dia kata negligible. So we can assume that the heat absorbed by the calorimeter is equal to 0. Okay, sometimes dia bagi juga. Dia bagi heat capacity of the calorimeter. That means you have to have this lah. Sama like this one. Exactly the same. Okay. Alright. So all in all, kita boleh relate that the Q system kita, bila kita conductkan, dia adalah combination of H2O, calorimeter and the reaction itself. This one, dia tak akan, that means there's no loss of heat. Tak ada loss of heat to the surrounding, which is equal to 0. Okay, so which is equal to 0. So the QH2O or the Q solution can be calculated as usual, MCS delta T, whereas for calorimeter, it will be heat capacity of the calorimeter times delta T. Okay, maybe you can look at one question here. Cuba tengok soalan ni. Identify, okay? All right, so we have naphthalene. So this is the amount of naphthalene, and then this naphthalene is burned in a constant volume bomb calorimeter. So we are using bomb calorimeter here. Okay? Consequently, the temperature of the calorimeter rose from 20 to 26 degrees Celsius. So obviously, the reaction release heat. Okay, they release heat, and then the water will be accepting and the calorimeter will be accepting the heat. Okay, if the heat capacity of the bomb is given as this, calculate the energy change for the combustion of naphthalene. Okay, did you see water and the mass of water given? No, dia tak bagi dekat situ. So kita guna apa yang ada lah. So mungkin dia dah combine. Water tu is already inclusive in this heat capacity. Sebab yang kita ada contoh tu dia pakai water. Ada sekarang ni calorimeter, bomb calorimeter tu tak pakai water pun. Okay, tapi tak apa, dia depends on whatever information is given to us. So Q reaction kita, which is naphthalene, the combustion of naphthalene. So since it release heat, so dia ada negative first tu. Okay, is equal to Q. Siapa surrounding kita? Okay, let's start from the system lah. Okay, surrounding. Okay, so Q system kita is reaction, betul tak? Q surrounding kita in this case is calorimeter, because calorimeter is the one that accept the heat from the reaction. Then yang ni nak cari kan, yang kita ada information at the moment, we have Cal, which is C delta T. Okay, insert lah. Dapat dah jawapan. Okay, another example. This one lah. Okay, you tolak kan dapat. Okay. Lupa. Soalan tanya apa? Energy change, guys. This is delta E. What you are calculating just now is Q. This is Q. You baru cari Q. Soalan tanya energy change, the delta E. Okay, so you kena make sure that the Q need to be divided by the mole of the substance given. Yang ni. Divided by naphthalene, the mole of naphthalene. Okay, that means kita dapat the information lah for 1 mole, what will be the, how much heat will be released. Don't forget the negative, okay? Don't forget the negative. How much heat will be released. Okay, alright, another example. That's why dia ada ni pergi cepat-cepat. Another example again is using bomb calorimeter, guys. This is for benzoic acid. For this time around, dia bagi 2000 gram of water. Dia bahagi pula. So you kena guna information yang dia bagi. So imagine bila reaction tu, water will be accepting 2000 gram of water and also the calorimeter. Okay, again soalan tanya energy change. So energy change is equal to Q over mole. So misi kita mencari Q of the reaction first, which is negative kan. You patut dapat negative value lah. Okay, alright. So Q reaction is equal to Q water, because dia release heat, betul tak? Q water plus Q cal. Kenapa ada tiba-tiba Q water? Sebab dia bagi information dekat sini. Okay, so MCS delta T plus C delta T. Masukkan all the information there. Okay, alright. So yang ni lah, you define dulu. So this is for QH2O. This one. Unit jangan lupa ya. And this one here is for calorimeter. And then you total up, you dapat this one. Totalkan ya. And then don't forget you nak cari energy change. Okay, so you bahagikan. Dapatlah. Negatif jangan lupa. Alright. Okay, so that is all. Kita stop dekat sini dulu. Unfortunately. Tak apa. Alhamdulillah. Kita ada sikit je lagi. Okay. Alright. Any questions so far, guys?
No, madam.
Madam, kalau enthalpy change pun bagi dengan mole kan?
Ya.
Okay.
Okay, bila enthalpy tu maksudnya, coffee cup. Okay, pressure, normal pressure. You use coffee cup. Kalau delta E, ini guna bomb calorimeter. Okay. Alright. Lagi? Ada lagi? Alright, so if there is no question, I think that's all for today, guys. Thank you everyone for your attention and Assalamualaikum. Bye-bye.